Imagine opening a book to find an entire chapter mysteriously ripped out. A chapter that holds critical details about how the story began. That's what geologists face when they encounter the Great Unconformity, a billion-year gap in Earth's history where crucial rock layers have vanished. How did this happen? What secrets lie hidden in this missing time? Today, we're diving into one of the geology's greatest mysteries to uncover what this gap tells us about our planet's dramatic past. The Great Unconformity. What's missing? The Great Unconformity isn't just a geological oddity, it's a glaring omission in Earth's history. Imagine a timeline of rock layers, each telling a story of ancient life and landscapes. Suddenly, there's a huge leap, a billion years gone without a trace. This striking phenomenon happens when older rocks are eroded, leaving a stark divide between what came before and the younger layers deposited on top. It's like an ancient library where someone burned the first few volumes, leaving scientists to piece the story together from scattered pages. Why is this gap so important? Because within it lies the answer to critical questions about Earth's history. What environmental upheavals caused such massive erosion? And what forms of life, if any, were lost to time? Building the geological record. To understand what's missing, we first need to grasp how the geological record is created. Over millions of years, particles like sand, silt, and clay accumulate, forming layers of sediment. These layers compress and harden into sedimentary rock, a natural history book filled with fossils and clues about ancient climates. Sedimentation is a fundamental geological process where particles, such as sand, silt, and clay, accumulate over time, eventually forming sedimentary rock. This process occurs as sediments are transported by water, wind, or ice and deposited in layers. Over millions of years, the weight of overlying materials compresses these sediments, leading to lithification, where they harden into rock. This gradual accumulation creates a rich geological record that captures various environmental conditions. Fossilization plays a crucial role in preserving biological remains within these sedimentary layers. When organisms die, their remains can become buried by sediments, protecting them from decomposition. Over time, minerals infiltrate the remains, replacing organic material and forming fossils. This process allows us to glimpse past life forms and ecosystems. Studying sedimentary layers is vital for understanding Earth's history, as each layer represents a specific time period, revealing changes in climate, sea levels, and biodiversity. Fossilization captures snapshots of past life, preserving creatures that once roamed Earth. But when layers are eroded or never formed in the first place, those snapshots disappear. The Great Unconformity interrupts this process on a massive scale, leaving geologists scrambling to reconstruct the timeline. Geologists like Nicholas Steno and James Hutton paved the way for our understanding of unconformities. Steno's principle of superposition, where older layers lie beneath younger ones, was a game changer. Hutton took it further with his discovery of Hutton's unconformity in Scotland, showing how erosion and sedimentation operate over vast timescales. In the Grand Canyon, explorer John Wesley Powell identified another dramatic example of the Great Unconformity. His explorations highlighted the geological history recorded in the canyon's layers, furthering our understanding of the complexities of Earth's geological timeline. Together, these figures and their discoveries have profoundly shaped the field of geology and our comprehension of unconformities. These discoveries revealed that Earth's history is far older and more complex than previously imagined, challenging early beliefs in a young Earth. One theory about the Great Unconformity points to a period of extreme glaciation known as Snowball Earth. Around 720 million years ago, the planet may have been encased in ice, triggering massive erosion as glaciers advanced and retreated. During this time, the planet may have been entirely covered in ice, leading to significant climatic and geological changes. This extensive glaciation could have resulted in substantial glacial erosion, which would have stripped away existing sedimentary layers. contributing to the missing geological record observed in the Great Unconformity. As glaciers advanced and retreated, they would have reshaped the landscape, erasing evidence of earlier geological periods. Following this dramatic ice age, the Earth experienced a remarkable transformation, leading to the Cambrian Explosion around 541 million years ago, a time marked by a rapid diversification of life. The melting of glaciers released nutrient-rich minerals into the oceans, creating an environment conducive to the flourishing of complex life forms. This connection between glacial activity and the subsequent explosion of biodiversity underscores the significance of the Snowball Earth theory in understanding the Great Unconformity and its implications for Earth's geological and biological history. This relentless grinding could have scraped away entire layers of sediment, erasing evidence of early ecosystems. But here's the twist. As the glaciers melted, they released nutrients into the oceans, possibly fueling the explosion of life that followed. The Cambrian Explosion, life's big breakthrough. Fast forward to 541 million years ago, and we hit the Cambrian Explosion, a time when life on Earth diversified at breakneck speed. From simple organisms, the first complex animals emerged, filling ecosystems with a dazzling array of life forms. What's fascinating is the possible connection between this explosion and the Great Unconformity. As glaciers melted, nutrient-rich minerals were released into the oceans, creating favorable conditions for the rapid evolution of diverse life forms. Thus, the Cambrian period not only represents a significant chapter in the history of life, but also serves as a critical link to the geological events encapsulated by the Great Unconformity. Could the dramatic environmental changes during Snowball Earth have set the stage for life's grand debut? Scientists believe the release of nutrients into post-glacial oceans might have jump-started this evolutionary boom. So why should we care about a billion missing years? Because these gaps hold the keys to understanding Earth's dynamic processes. How continents form, erode, and reshape. How climates shift, and how life adapts to cataclysmic change. The Great Unconformity is more than a mystery. It's a reminder of Earth's resilience. It teaches us to look deeper, to question the gaps in our knowledge, and to appreciate the interconnectedness of geological and biological history. Today, we've explored one of Earth's greatest enigmas, peeling back the layers of the Great Unconformity to uncover its profound implications. But the mystery is far from solved. Scientists are still uncovering new clues, and each discovery brings us closer to understanding our planet's hidden past. If you're as fascinated by Earth's secrets as we are, subscribe to our channel and join us for more journeys through time. Like this video, share it with fellow curious minds, and let's continue exploring the wonders of our world together. Thanks for watching, and see you next time.